Hi, and welcome to the 10 square meter workshop. Today I'm going to attempt something that may not be possible. It's not available commercially as far as I can see. That usually means it's not practical. So join me on a journey and we'll see, coming up after this. When it comes to dust extraction, there's basically two forms. The vast majority are powered by something like this. It's a brushed motor, can work on either AC or DC, and can run up to 10 to 20,000 RPM, which is what's needed for driving this fairly small impeller. They're noisy, inefficient, and get quite hot. And they're quite cheap. They're called HPLV. That's high pressure, low volume. They can suck quite hard, but can't shift a lot of air. The alternative is a low pressure, high volume system. This is usually driven by an induction motor. The problem here is, although it's got plenty of power and is quite efficient, it can only turn quite slowly. The speed of the mains coming in. That's 3000 RPM in most of Europe, 3600 in America. And this just isn't really fast enough. The size impeller you need is quite large, and in fact if you wanted the same sort of pressure you get from a smaller system, it would be huge, several feet across. So, is there another way? But how about something in between? A medium pressure, medium volume, which would be much more use for most workshops. Well, they're not available. In fact, it's normal to add another, or maybe two more, devices to increase the total volume. This is not really a good approach. 3 impellers is the most you can have if you want to run it from a 3-pin plug. And of course the plumbing gets a bit complex if you want a cyclone. One answer is to drive the motor with an inverter, so you can increase the frequency. This is a spindle, as used in CNC machines. This is a 2 kilowatt version. You can get even higher. And it can be driven up to 400 Hz. That's 24,000 RPM. Can this be the answer? Getting an impeller to fit can be difficult. They're not really available, so I 3D printed one. Now I was concerned at whether it could take the strains. So, surrounded by concrete blocks, I ran this up to 18,000 RPM. That's as far as I dared. And yep, it's still in one piece. So there's some hope. The size of the impeller means it should be able to shift about 4 times the volume. We shall see. I originally built this because I was trying to make a quieter dust extractor. And I found that although the motor is a lot quieter, then the noise of the air through the impeller becomes the dominant side. And it's not really any quieter. So I abandoned the project. However, that can miss the point. What we're after is more flow at good pressure. So why not carry on? I shall be using the bin and cyclone from a previous project. I designed the impeller to be a siding flit into the top of the cyclone. So all I need to do is build support and a frame to prevent any injuries should the impeller fly apart. First step is to build a strong support frame. This is also recycled from a previous project. It doesn't have to be pretty. This is a proof of concept build. This is the inverter unit I will be using. Remarkably cheap these days. Here is the spindle impeller unit fitted on top of the cyclone. The front and back parts are now in, so I should be protected against shrapnel. Time to give it a run, just to make sure it works. Okay, let's give it a try. (6,000 RPM). Okay, that was 10,000 RPM. That'll do for the moment. Here is a view of the exhaust route before I attach the end panel. The square outlet will have a HEPA filter fitted. Boxed up and ready for the filter, which I can't fit yet because Amazon haven't delivered it yet. View from the other side. Time to wire it up. And here it is, wired up and ready for testing to begin. Yes, it's quite tall, but it has a very small footprint. That's often what's most important in the workshop. Final step was to seal all joints with silicone sealer. For test purposes, I'm going to compare it with this can style shop vac. It's sold under various brand names. You probably recognise it. It's quite common. This should give a real world evaluation. I shall be using an anemometer to measure the flow rate, using a 50mm inlet in each case. This is not supremely accurate, but it's a good comparison. I measured the airspeed through the SIP unit through a 50mm orifice. Then on the new unit, which is the same size. I plotted the new unit in a range of speeds in order to plot a graph. The response was pretty linear, as you'd expect from the physics of the thing. And this is the resulting graph. The right hand side is extrapolated. My meter ran out of range. The first thing to notice is the SIP unit met its specification, shown by the vertical line. The second thing is that within the speed I was prepared to take, I could get up to twice the output. 3 times if I was prepared to run to full speed. So, was the experiment a success? Well, yes and no. I can get about twice the extraction rate, but any more than that would challenge the hoses of a 50mm outlet cyclone. Really, to get any more, I'd need a bigger cyclone, and that starts getting a big project. You really only need that level of suction for big machines, big table saws cutting large pieces of timber, planer thicknesses, spindle moulders. If I ran those a lot, I would definitely think of building one like this, only with a bigger cyclone. However, I don't. Just for fun, let's watch it suck some dust. Fire up. I call that pretty effective. So, in conclusion, I think this system, fitted with perhaps a slightly bigger cyclone, 75mm, it provides a perfectly viable system for a medium-sized workshop where you want a single extraction system for all tools. It's not something my workshop needs, but I think I learned an awful lot doing this. I hope you found it informative too. So why not subscribe to my channel, and I'll see you next time. Bye for now.